So to figure out what it means to multiply one matrix by another, again, all we know at this point, going back to our slide of the things we know how to multiply a matrix by a vector. But what we don't know yet is how to multiply a matrix by another matrix. But if there's any justice in the world, we should be able to determine one from the other. Knowing how to multiply a matrix by a vector should tell us how to multiply a matrix by another matrix. And that's indeed what's going to happen. So, let's start with just an example. Suppose I'd like to know how to multiply the matrix, 2, 1, 1, 2. So here's a nice square, friendly 2 by 2 matrix. And I'd like to multiply that matrix by 1, 2, 3, 4. Another nice, friendly square matrix. And I'd like to know what that product is. Well, we don't know how to multiply a matrix by a matrix. But since we do know how to multiply a matrix by a vector, let's throw a vector in here. Maybe x, y. Because now we have a product, namely the product of that xy by the matrix 1, 2, 3, 4, we can figure out what that product is. And when I multiply a matrix by a vector, what kind of an object do I get out of that product? I'm going to get another vector out of that product. In fact, if I want to keep my colors consistent, when I multiply a matrix by a purple vector x, I get a green vector b. So I'm going to get a vector out of that. And then I'll just have to multiply that vector by 2, 1, 1, 2, and I know how to multiply a matrix by a vector, so we'll have it. So once we throw that vector in there, we have a place to start, because we can multiply the matrix on the right here by the vector xy. And how do you multiply a matrix by a vector again? Distribute the vector into the columns and form a linear combination of those two columns. So x times the vector 1, 2, the first column, 1, 3, and y times 2, 4, and then add those together. And I'm actually going to not make that any simpler for the moment. I'm going to leave that just as it is. And then maybe I'll make a second copy of it off to the side. So we can look at this from a couple different perspectives. So over here, let's actually simplify this. X times 1, 3 plus y times 2, 4 ends up being x plus 2y and 3x plus 4y. And then the last step here is we've got to multiply by the 2, 1, 1, 2 matrix. So I'm going to do that in both places here. Let's do it on the right-hand side first. So on the right-hand side, how do I multiply this matrix by this vector? I'm going to again take a linear combination of the columns. The first column 2, 1, and the second column 1, 2. Except what are the coefficients of my linear combination this time? When we did our last linear combination, we took x of the first column and y of the second column. So when we take this linear combination, how much of the first column do we need? Since the first entry of our vector is x plus 2y now, that's how much of the first column we're going to take. X plus 2y times the first column. And then likewise, 3x plus 4y of the second column. Added together. So we have a little more arithmetic to do this time. Twice x plus 2y, that's going to be 2x plus 4y. And then 3x plus 4y times 1 is going to give me 3x plus 4y. And in the second component, 1 times x plus 2y is x plus 2y. And twice 3x plus 4y, 6x plus 8y. And now, I'll just combine the like terms in this to ultimately get, what am I going to have here? 2x and 3x are going to give me a 5x. 4y and 4y, 8y. Down in the bottom, x plus 6x and 2y plus 8y. So let me set this apart in a little box down here. So there's what we get when we just brute force out the product of the matrix on the right by the vector, which becomes a new vector, and then the product of the matrix on the left by that vector. So can we look at this answer and deduce from this answer what matrix would accomplish that product? So what matrix multiplied by xy would give us 5x plus 8y in the first component and 7x plus 10y in the second component? What matrix belongs here to make this happen? 5, 8, 7, 10. And so we surmise that the product of these two matrices is precisely the matrix 5, 8, 7, 10. That's the very longhand way to figure out what the product of these two matrices is. Throw in a vector because we know how to multiply a matrix by a vector, follow through all of that arithmetic, and then at the very end say, well, okay, if I don't have that vector there, then what matrix would I have been talking about? And here the answer is 5, 8, 7, 10. So now we have to come up with a way of doing this without all of this work, without introducing xy only to take it away again at the end. And that's where the matrix multiplication algorithm comes from. Let's look on the left-hand side of our divide here. So remember 5, 8, 7, 10. I'm going to keep it on the left, but I'm going to erase this part on the right. So when I multiply here this product, because matrix multiplication is linear, it distributes over scalar multiplication and it distributes over addition. What that means, we learned that when we talked about linear transformations, because every linear transformation can be represented by a matrix, and linear transformations distribute over linear combinations. It means I can rewrite this as x times the matrix 2, 1, 1, 2 times the vector 1, 3 plus y times the same kind of thing, 2, 1, 1, 2 times the vector 2, 4. And again, because we know how to multiply a matrix by a vector, we know how to do each of these matrix vector products. They're going to give me 1 times the first column, 2, 1, plus 3 times the second column, 1, 2, and then at the end, same thing, y times twice the first column, 2, 1, plus 4 times the second column. And what's different about this way of computing is that now we have all of our x's together in one place, and we have all of our y's together in one place. Like the whole first term here is a coefficient of x, and the whole second term here is a coefficient of y. So that what we're really looking at is respectively the first column of the product and the second column of the product. In fact, if we do out this arithmetic, you'll find that 1 times 2, 1, plus 3 times 1, 2, is indeed 5, 7. And then likewise, 2 times 2, 1, plus 4 times 1, 2, is 8, 10. So we're getting a little closer here to an algorithm, because now looking at where the coefficients of this linear combination came from, the columns here came from our first matrix, 2, 1, 1, 2. That much is obvious. But where do the coefficients come from? This 1 and this 3. Where were those?
From the other matrix.
From the first column of the second matrix. Right. So let's focus on one of the numbers in our product. Let's focus on this 8 for a second. And let's try to reverse our steps here, trace them backwards, and figure out where that 8 must have come from. So we're going to be detectives here for a second. So where's that 8? First of all, we know it's got to come from this second term here, because it's attached to a y if we were to look at it, our old answer. So it comes from there. But specifically, it must have come from the first coordinate, or the first entry, because after all, it's part of the first row of that final matrix, the first row of the second column. So it must be the 2 and the 1 from my original matrix multiplied respectively by 2 and 4. Those came from my second matrix. So looking back in our original problem, we can find the locations of those. Specifically, the 2 and the 1 from my first matrix are these two coefficients. And the 2 and the 4 from my second matrix were these coefficients. So where does this 8 come from in the matrix product? It came from the product of this 2 combined with that 2, added to the product of this 1 with that 4. So what have we done here? We've gone across the row of the first matrix and down the column of the second matrix and taken the products of the elements we find and added those products together. And that's the matrix multiplication algorithm that people know and love. It's the matrix multiplication algorithm that you may have seen before. High school algebra 2 and pre-calculus will occasionally, if you do matrices in high school, they'll talk about this algorithm with you. And you can use the same algorithm for multiplying a matrix by a vector. But the reason that it works is because of everything that's here on this slide. It's because of the definition of how to multiply a matrix by a vector, and crucially, the linearity of matrix multiplication. Without the linear part of linear algebra, we wouldn't have been able to break apart this, we wouldn't be able to distribute this matrix multiplication across the scalar multiplication and addition that's happening in the green set of parentheses there. So this means that we can find the product of any pair of matrices now. Just by taking a row out of the first matrix, a column out of the second matrix, and multiplying and adding. So the first entry of the row times the first entry of the column, the second entry of the row times the second entry of the column, and so on and so on. Third entry times third entry, fourth entry times fourth entry, whatever, and then just adding those all together, all those products together.